Okay, so we've finished talking about more in depth the formulas for different forces and how they differ, like static and kinetic friction and stuff like that. So now the last two sections of chapter 5 are just a couple applications of Newton's laws. So 5.7 is about interacting objects, which is kind of a confusing in-depth look at Newton's third law. So there might be some things that you don't quite fully understand, but that's okay. Newton's third law can get really complex. So we'll just have a brief little discussion about it now and go on from there. So a quick little review. Newton's third law states that all forces occur as an action-reaction pair. So they recur as an action-reaction pair of forces. They always act on different objects. So if object 1 pushes on object 2, then object 2 pushes back on object 1. But the two members of an action-reaction pair are they're going to point in opposite directions but have equal magnitudes. And we kind of took a look at that before, so now let's spend a little bit more time talking about that now. So here is an example of there's a hand, and that hand is pushing box A. But as it pushes box A, if we were to look at analyzing A's motion, we would have to understand all the forces acting on it. So A is being pushed on by the hand. So if I were to draw a quick little free body diagram, there is a push of the hand onto A, as well as, of course, the weight and the normal force. And that's going to cause acceleration. But the other thing we got to kind of think about is how much it accelerates isn't just based on A's mass, but also based on B's, because we need to think about that as A pushes on B, B, according to Newton's third law, pushes back on A. So there's this force of B on A right here. And if we do the same thing with block B, now it's got its weight, which is larger than A's, its normal force. There's the force of A on B, but it's also going to push back on A. B on A. Okay, so as we look at these, the forces on A and B, they're not independent on each other. The force that B on A, so the block B acting on block A, and the force of block A acting on block B, they're an action-reaction pair, and therefore, since they're in contact, they have to have the same acceleration. And that makes sense. Like, these two objects are connected to each other. So as I'm pushing one, because there's that action-reaction pair, the other one must also be moving. But the point is that we can't solve for the motion of one of the block without considering the other one. If block A was the only block there, it would accelerate at some rate. But since block B is also there, it's also causing forces to act on A, and we have to take in that account. Okay, so what does that mean? Well, let's go. It means that we're going to have to start considering not just the mass of one object, but you'll see me, especially as this unit continues, that the force, the net force, it no longer equals the mass, but it's the mass of the system, not times the acceleration, but times the acceleration of the system, which seems kind of trivial that I'm just adding those subscripts. But if I think even back to the Atwood machine experiment where we had the masses hanging off the edge of the table, those masses and the cart accelerated at the same rate. So as we think about Newton's third law, that's what we're going to have to consider, is that all the forces act on a system, and as I increase the mass of the system, the overall acceleration will decrease, and we'll talk about that a lot in the last section, which is on ropes and pulleys. All right, so here's a quick check. Considering the situation in the figure, which forces is an action-reaction pair. So I have all these forces going on, which is actually really confusing. But I have to look and say, if A acts on B, B acts on A. So which one is the action-reaction pair? As I go through the options, the normal force on A due to B and the weight of A. So A has this force going downward, and B pushes back up, and that is why B is the correct answer. Taking a look at the other ones, the tension of the string and the friction acting on A. A is pulling, or the string is pulling on A, then the action-reaction pair would be A pulls back on the string. So that one's not it. The normal force on A due to B and the weight of B. So B pushes up on A, but then B also goes down. That's not an action-reaction pair. And finally, the frictional force acting on A and the friction acting on B. Those are two different objects, so it's not an action-reaction pair either. All right, here's another one. Boxes A and B are being pulled to the right on a frictionless surface. This is getting back into what we're talking about. Now, tension 2 is pulling both block B and block A. Tension 1 is being pulled on by B, but it's only pulling block A. So therefore, tension 2 is actually greater than tension 1. So these can get kind of confusing as we get into talking about that, but we'll summarize that up in just another minute. Here's another ranking task. So boxes A and B are sliding to the right on a frictionless surface. Hand H is slowing them down. Box A has a larger mass than box B. So we know there's an action-reaction pair with the hand on block B. So those have to be equal and opposite. So B on the hand is equal to the hand on B. But then A is pushing on B, so B has to push back on A. And those are an action-reaction pair. But since the hand is causing the acceleration, that's going to be the greater of the two forces.